Hello students. Welcome back to my channel, the Goddess of Econ. The topic that I will cover today is only for those students at the advanced level, so if you are looking for Econ 101 lecture videos, please refer to other categories of my channel. So, what am I going to cover today? I will cover a subsidiary theorem in economics, often appearing in the field of producer theory, called Hotelling's lemma, named after the famous American mathematical statistician, Harold Hotelling. So, if you are interested, please follow me. Okay, let's denote the production function as y. Y is a function of inputs to production, namely K and L. Here, K refers to capital, and L refers to labor. The cost of capital is the interest rate, R. And the cost of labor is the wage rate, W. So, given these, the firm's objective can be written as the following. Maximize the profit by choosing the optimal quantities of capital and labor. Here, P times Y is the total revenue, whereas the sum of R times K and W times L represents the total cost. So, the total revenue minus the total cost is the profit, and the firm's objective is to maximize this. Simple, isn't it? Now, let's solve this profit maximization problem together. As is the case with any optimization problem, at the interior maximum, we know that the following first-order conditions will hold. That is, price times partial derivative of y with respect to k minus its cost, which is r, equals 0. Similarly, price times partial derivative of y with respect to l minus its cost, which is w, equals 0. And using these first-order conditions, we can derive the solutions to this problem as follows. The optimal level of K comes out as a function of the prices of inputs and the output, that is, R, W, and P. Similarly, the optimal level of L comes out as a function of the prices of inputs and the output, that is, R, W, and P. These functions are called input demand functions, or equivalently, factor demand functions. They simply represent the optimal level of each input given R, W, and the output price, P. Now, let's put the solutions to this problem, that is, input demand functions, back into the original objective function and examine its properties. Okay, here is the objective function. Remember, the solutions we have obtained are optimal levels of K and L, both expressed as functions of R, W, and P. If we put them back into the objective function above, then we have the following. Although it may look a bit complicated at first glance, it is actually not. All we did was to replace every K and L in the objective function with K star and L star. In other words, we just plugged in the optimal values of K and L, each expressed as a function of R, W, and P. And since optimal values of K and L have been plugged into the profit formula, the resulting profit function, that is, pi star should give the maximum profit given values of R, W, and P. Hence, the function pi star above is often called a maximized profit function, or a maximum value function, as it always returns maximum profit given R, W, and P. Okay, we are halfway there now. Please bear with me a little longer. Next, now given this maximized profit function, or maximum value function, or pi star as written above, let's do one more exercise. That is, let's differentiate this maximized profit function with respect to one of the input prices, for example, R. Are you guys ready? Okay students, let's go. The partial derivative of pi star with respect to R is price times partial derivative of y with respect to k star times partial derivative of k star with respect to R, plus price times partial derivative of y with respect to L star times partial derivative of L star with respect to R, minus k star minus R times partial derivative of k star with respect to R, minus W times partial derivative of L star with respect to R. It may look long and confusing, but please note that all that was used was a simple chain rule. I am sure most of you students can do this exercise yourselves, if you have basic knowledge in calculus. Now, let me rearrange the right side of the equation, by factoring out the partial derivative of K and that of L. Now, this equation is essentially the same as before, except that I have factored out the partial derivative of K and that of L. Students, do you see anything interesting here? Let's look carefully at the inside of the two parentheses. Don't they look familiar to you? Yes? No? In fact, We have come across the expressions in the parentheses already in page 2, when we obtained first-order conditions for maximization. Let me bring back the first-order conditions here for your information. Do you see it now? According to the first-order conditions, the expressions in parentheses should become 0 at the optimum. And anything that is multiplied by 0 is just 0. Quite a neat result, isn't it? What this all means is that the first two terms, on the right-hand side of the equation, all become 0. So, we're essentially left with the last term only. In summary, by differentiating the maximized profit function with respect to R, this result says that you can get the demand function for capital right away. Well, to be exact, you get the factor demand function times -1. This is indeed quite a neat result. If you differentiate the profit function or the maximum value function with respect to the price of an input, you can derive the factor demand function for that particular input right away. Okay, maybe I will stop here and make this video part 1 of my Hotelling's Lemma lecture, as it is getting longer than I expected. I will come back with the second part of the lecture very soon, so please do visit again if you want to have a complete picture of Hotelling's Lemma. See you soon, and God bless all.